In this module, we'll learn about relational databases and SQL. So why are we learning about databases and SQL? Databases are perhaps the single most important class of corporate applications. Databases are surprisingly powerful data modeling and analysis tools in situations where spreadsheets fall short. Students who plan to work in management consulting will soon find this out. Microsoft Access is a great example of how easy it is to build powerful applications without the need of background in technology. But in this class, we are going to learn SQL directly. In the previous Tableau labs, the learning objective was to learn to fish. That is, enough hands-on practice and how to figure out how to do things by yourself using the various resources available these days. In this SQL module, the objective is to learn to think about extracting information from a database. We'll briefly talk about what is a relational database, what is behind the EHR, and then start to learn how to leverage data to improve operations in hospitals. Many of you will just get the taste of this, but some of you may learn to start to fish. We will cover 3 topics in this module. What is a database? What is a DBMS, standing for Database Management Systems, and an introduction to SQL, which is the programming language used to work with DBMS on computers. We will mostly focus on how to retrieve information from a database. So what is a database? The boring answer may be a structured collection of data. For example, a telephone directory which has a list of names and phones in your city. But a more insightful and useful answer may be it's the digital representation of the real world. Your EHR is the digital representation of all the services your hospital provides. The database is a data-centered mirror of an organization's business processes. Often, your EHR reflects the many processes in your hospital. The structure of the data reflects organizational processes, and the content of your data reflects the organization's history. So the EHR in your hospital will reflect all of the history that happened at your hospital, as well as the structure of how your organizational processes work. So what is the data needed to represent the real world? First, there are entities we need to maintain information about, such as people, places, things, or events. Examples may be employees, patients, products, services, visits, and warehouses. Then there are the attributes about these entities that we would like to store information on. These would be characteristics or qualities of particular entities. For example, employee social security number, patient's address, product unit price, diagnosis of the visit to justify the claim, or charges for the visit. Finally, you would like to store the information on relationships among these entities. For example, certain patients are seen by certain doctors. The basic data model is a table in a database. Each row represents one entity. Each column represents one attribute. Thus, each cell stores data about an attribute of an entity. For example, in the table below, you have the patient entity table, with each row representing one patient. For example, row 2 represents Edwin, and each column representing one attribute. For example, column B represents the first name of all entities. Here is an example of a database sitting behind an EHR. In this example, we see entities such as patients, visits, medications, and providers. And these entities are stored using a unique ID for each of the entities. In addition, we see attributes about these different entities. For example, first name and last name of providers and patients. So what's the difference between spreadsheets and databases? We all use spreadsheets on a daily basis to keep track of lots of things. Spreadsheets are great for keeping track of data for one type of entity that is simple. For example, keeping track of participants at a conference, or students in a class, or customers of a company. However, it is difficult to keep track of multiple different entities in a spreadsheet. One difficulty is that a visit is essentially a relationship between one patient and one or more service providers, medications prescribed, and labs ordered. In fact, storage of information is not even half the story. The reason we build databases is in order to easily retrieve information to answer questions that support clinical and managerial decision-making. For example, who are our top 10 most costly patients based on their total cost during hospital visits in 2014? Can you do this using a spreadsheet? Can multiple people access it at the same time so they can all ask questions? Do you see how things get complicated when we want to keep track of several interrelated entities? For example, keeping track of relations between patients, providers, medications, and visits. You tried it in assignment 5. How was it? You could mostly figure out the relevant data. But to keep all the sheets, to fully incorporate all of the relationships, and always maintained correctly, how much work would that be? Spreadsheets and databases are used for different purposes. The pros of a spreadsheet is that it's very human-friendly and flexible. It's a place where people keep information and their own data as almost personal notes. You can store data in however way you want and however much you want to do that. This flexibility comes with consequences. That is, the cons of a spreadsheet is that it is not computer friendly. This is because it is very difficult to keep track of data that strictly follow certain rules, such as protocols and standards. If rules are not strictly followed, computers cannot do much with the data. In addition, keeping multiple sheets consistent, that is, the relationships between the different data getting hold, is difficult. Also, concurrent access by many users is difficult. And finally, tracking changes is difficult. That is, if you made a mistake and you need to track back if something went wrong, is quite difficult. In comparison, a relational database supports storage of a data as a set of interrelated tables that strictly follow all the rules. Each table stores data about a set of entities. Each table row is a record about one such entity, and each record column is a field specifying an attribute of this entity. Each record has a field that acts as a unique identifier of an entity, usually an ID number, and relationships among entities are specified by referring to this unique identifier from other tables. A DB schema is the blueprint of the database, holding information about the design of tables that store information about the entities and attributes, as well as the relationships between the different entities. Here is the EHR database again. Can you identify the entity that each table represents? The attribute that each column represents? Do you see the unique IDs for each entity? Do you also see that tables 2 and 3 have more than one entity ID? For example, table 2 has 3 entity IDs for visits, patients, and providers. Table 2 is the visit table where one row represents one unique visit. Thus, the visit ID is the primary key, which represents the unique visits. The other IDs, patient ID and provider ID, are called the foreign key. A combination of primary and foreign keys are used to implement and enforce relationships between entities in a database. Every table must have a field whose value uniquely identifies each row in the table, such as Social Security numbers for people and ISBNs for books. That field is called the primary key and is marked in the field list. The primary key represents the entity of the table. Foreign keys are used to identify records or entities in other tables according to the relationship. The foreign key attribute in a table uses the primary key of another table. Referential integrity is used to keep the database consistent based on these types of relationships specified by primary key and foreign key. For example, if a patient is deleted from the patient table, all visits with this patient involved must be deleted from the visit table. This is referred to as cascading deletes. Similarly, Inserts are not allowed in the visit table for patients that do not exist in the patient table. This keeps the database consistent. A database schema is the design of the database. It stores information about exactly what tables make up the database and what variables make up the table, as well as how these tables are related using the primary keys and foreign keys. Here is an example of a database schema with 6 tables. Crossfoot notation specifies the relationship between the tables. It refers to the lines that connect the tables with endpoints representing different relationships, such as one-to-only-one or one-to-many. In an EHR, one-to-many relationships are seen in the patient-to-visit tables. One patient has many visits. So what is a database management system? A relational database management system is a software that allows the creation of a relational database. It supports specialized languages, typically SQL, for easy retrieval of data from a set of interrelated tables. It supports easy construction of a graphical user interface on top of the database so people can interact with it more easily. It allows very large tables to be managed, and it provides security, fault tolerance, and multi-user support. The best example of a DBMS in the health sector is the EHR. There are many different database management system softwares, such as SQLite, using MySQL as the backend with the PHP front-end GUI. Microsoft has both the SQL Server and Access. Access is something that's available through the Office suite to many of us. Oracle is the most well-known, probably, and the most expensive database management system, and IBM has DB2. ODBC stands for OpenDB Connectivity, and it is the middleware API that talks to different database systems. All of these DBMS uses some variation of SQL as its standard language, and many of them have different variations on the standards, but importing and exporting via standard protocols are easy. The most universal file format is CSV, called the comma-separated values, where each value is separated by a comma, and often the first line is header information. This is a typical software stack of a DBMS, where at the back end, the bottom layer is the database. It can be any one of the available options. The ODBC is the translator layer in the middle. And then the DB applications is the front end, which is the web interface, or sometimes called the GUI, that the users interact with. There are 4 most desirable characteristics of a transaction in a database management system called ACID. Stands for atomic, consistent, isolated, and durable. Atomic transactions are such that the transactions is either entirely completed or makes no change to the database. Even if an error or a hardware fault occurs mid-transaction, the database will not be left with a half-completed transaction. For example, if an ATM fails in the middle of depositing a check, the bank database would not have a record of the deposit halfway. Consistent transactions ensure that the database is left in a consistent state after the transaction is complete, meaning that any integrity constraints such as unique keys, foreign keys are checked and must be satisfied, or the transaction will be rejected. Isolated transactions are invisible to the other users of the database while they are being processed. This is important for concurrent use by many users. Finally, durable transactions guarantee that they will not be rolled back after the caller has committed them. Early relational database management systems couldn't always guarantee all 4 of these requirements with their transactions, but modern counterparts can usually provide ACID transactions even in the event of power or hardware failure. There are many common programming languages and software to communicate about data. In this class, we've used Excel and Tableau so far, and will now move into SQL. R, Python, SAS, Data are some of the other common languages. Starting this week, we'll start the SQL labs. In this class, we will be using the DB browser for SQLite. For your SQL labs and assignments, you will have to install the app. There is a portable app version that does not need to be installed, and all you need is the one file. You can find details in the first SQL lab that you will be doing this week. If you have problems in using your own computer, you can use the lab computers by downloading the portable version.